So as we were just saying, the traditional way of looking at second order derivatives is with equations of motion. So we'll do a couple of problems like that. So the standard name for the function for position, believe it or not, is the letter s. And that comes from the Latin word for site that you see also like in our word situation, or where are you situated. So that's what we're going to use for position. That's s. Then there's velocity, which is the rate of change of position. So that's s prime. And since it's a rate of change, it can be positive or negative. So velocity, as we discussed one other time, is different from speed in that velocity has direction. So velocity can be positive, negative. Speed cannot be negative. Then there's acceleration, which is the rate of change of velocity. Right? If you're just traveling along at a constant velocity, you're not accelerating at all. And since it's the rate of change of velocity, and velocity is the rate of change of position, acceleration is actually s double prime of t. And you can keep going beyond that. So do you know what s triple prime of t is? The rate of change of your acceleration. So if you're accelerating in a smooth way, you don't feel this. But if you're accelerating in an erratic way, you feel a jerk. And that is actually what s triple prime of t is. It's called the jerk. And then s quadruple prime of t has its own name. It's called jounce, Jounce. You don't need to know any of these beyond this. Or snap, sometimes people call it. And then if you're a fan of American breakfast cereals, once you see that the fourth derivative is called snap, what do you want the fifth and the sixth derivatives to be called? You would like them to be called crackle and pop. And there is, in fact, an effort among some physicists to get them named snap, crackle, and pop. And if you don't know this reference to snap, crackle, and pop, you can probably look up a video about Rice Krispies on YouTube, and you will see that. Let's do a couple of examples here. So you suppose you're driving along in a car at 90 feet per second when you put on the brakes, and the brakes cause you to decelerate at 30 feet per second per second. Some people like to write this as per second squared. That's fine. It means the same thing. Until the car stops just of its own power, not by any crashing into anything. And we'd like to sketch our three big functions: acceleration, velocity, and position. Let's start with the easiest one. We have a constant deceleration of 30 feet per second per second. So the graph of acceleration is constant. Should it be constant at positive 30 or at negative 30? If it were constant at positive 30, since acceleration is the derivative of velocity, that means velocity would be increasing, right? But that's not what's happening. We are decelerating. You're putting on the brakes. So the acceleration starts down here at negative 30 and just stays there until the car stops. So now let's try to sketch velocity. So we already know the derivative of velocity is always negative 30. So what does it mean for a function's derivative to always be negative 30? That means that the slope of the velocity function is always negative 30. Now, how many such functions are there that have a slope of negative 30 always? There's infinitely many, right? Because if we know the rate of change, as we've said, going backwards, we don't know the actual position, the height of the original function. All we know is its shape. So we know the shape of this is a line with a slope of negative 30. Do we have enough information in the problem to decide which of those infinitely many lines with slopes of negative 30 is the one that we want here? And the answer is yes, we do, because we know that at the start of the problem, at t equals 0, the velocity is supposed to be 90. So that lets us pin down which of these infinitely many functions is the one that we're looking for. So we're starting here, going along at a slope of negative 30 until the car comes to a stop. And how many seconds should it take for it to stop? You're starting at a y value of 90. Your slope is negative 30. So this should take 3 seconds until you get down to a velocity of 0 on the t-axis. And then we want to go and sketch position. So we know that the derivative of position, right, v of t is s prime of t. So the two important things that we know about s prime of t are that s prime of t is positive above the x-axis, and s prime of t is decreasing. So if you look back to your useful chart, if the derivative is positive and decreasing, what does that tell you about the graph of the original function? This is saying that the slope is positive and getting less positive. That means this function should be increasing and concave down. Now, we're not told where to start this function, so it doesn't really matter where you start it. You could start it right at the origin and be increasing and concave down until you get to there. You could start it above. Those are all fine. What we don't have enough information to do yet is to figure out actually how far the car has traveled. By the end of the semester, so this is something you can look forward to and you can measure your progress that way, by the end of the semester we will be able to figure out what the height of this function is there. In other words, how far the car has traveled. If you have memorized some formula from physics class to do it, we will be able to figure out where that formula came from so that you can really understand it instead of simply memorizing it. But this is what these three graphs will look like. And let's do one more. So that first example, we had motion horizontally, side to side. Now we're going to look at one that has some vertical motion. So suppose that a rock or any other object is launched from ground level with an initial vertical velocity of 49 meters per second. And once the object's in the air, the only important force that acts on it is gravity, which causes a downward deceleration, a downward acceleration or a deceleration of 9.8 meters per second. We want to do the same thing like we did last time, sketch the graphs of acceleration, velocity, and position. So we'll start with the easy one. We have a constant deceleration, so that's at negative 9.8, and it just stays negative 9.8 the whole time. Sometimes people think that the acceleration changes whether the object is going up or going down. No. The Earth's force does not care anything. The Earth's gravitational force doesn't care whether the object is going upward or downward. It doesn't really care about the object at all. It's just constant at negative 9.8 meters per second per second. So that tells us that the slope of the velocity graph is always negative 9.8. So that means that the velocity graph is going to be a line with a downward slope of 9.8. And again, the question is, of all the infinitely many such lines, can we choose the one that goes for this problem? And here again, we have enough information to do that because we know the initial velocity is 49. So we know we're starting with a velocity of 49, going downwards with a slope of 9.8. When we touch the axis here, what does this represent? Is that when the object hits the ground? It's not when the object hits the ground because the velocity has been what this whole time? The velocity has been positive all the way here, meaning the object is going up this whole time. Now, for the first time, the velocity is 0, meaning the object has gotten to the top, the velocity is 0. Now the object's going to start to fall. So we're only halfway through. So what is our time so far? If you go down 9.8 units every time you go over 1 unit, you can check this for yourself, after 5 seconds, you'll be back down to 0 there. So now what does the graph of velocity do? Does it keep going underneath the t-axis or does it bounce up? Remember that velocity is different than speed. So the correct answer is that the graph will keep going underneath the t-axis like this. This is all supposed to be one nicely drawn line with a slope of negative 9.8. When the object is going downward, its position is decreasing. And we know that if something is decreasing, its derivative had better be negative. So since velocity is s prime of t, and we know that after 5 seconds, s is decreasing, the object is falling now, this graph has to be negative. If you drew this graph up above, you'd either be drawing a graph of speed, which is not what was asked for, or you'd be indicating that the object went up and up and up, slowed down, got to a point, and then started going up some more, which is not what happens. You can go outside and try this on your own. Now let's sketch the graph of s. So in this case, do we know where to start the graph of s? And in this time, the answer is yes, because we're launched from ground level. So we know s of 0 is 0. And the first 5 seconds look the same as the first 3 seconds of our previous example, because s prime is positive and decreasing. So according to our chart, s should be increasing concave down. Now the second part of the graph, s prime is still decreasing, meaning s is still concave down according to the chart, but now s prime is negative, meaning s is now decreasing. And when do we hit the ground? If you go up for 5 seconds, you go down for 5 seconds. So we hit the ground at time t. Again, what we don't know is what was the highest point that the object reached, but by the end of the semester, we will have learned enough calculus to be able to answer that question. And now we have an applet for you to experiment with changing the force of gravity. You'll have such extreme power. You can change the force of gravity, change the initial velocity of the object, all sorts of things, and try to predict before you change the sliders how these graphs are going to change. If you make gravity stronger, what should happen to this graph? What should happen to this graph? If you make the initial velocity greater, what should happen to this graph? What should happen to this graph? So please go ahead and play around with that.